Hello Internet, welcome to another tutorial on network analysis and synthesis. We are covering maximum power transfer theorem, and in this tutorial we'll specifically focus on a numerical, and we'll see the importance and significance of maximum power transfer theorem by solving this numerical. If you look at the statement of the problem and the network, you'll find that the load resistance is R, and we need to find the value of R such that maximum power is transferred to the load. And once we find the value of R, we'll need to further find the value of power, the maximum power which is delivered at the load. Now, in order to find the value of R, we'll need to reduce this circuit into its Thevenin's equivalent circuit, where R would still remain at the position of the load, and we'll need to find R internal or R Thevenin along with VTH. And once we do that, the next step is to equate R to be equivalent to R internal. If you keep the value of R is equivalent to R internal, or the Thevenin's equivalent resistance, then maximum power transfer will happen. And finally, we'll find the current in this circuit, and that current will help us find the maximum power dissipated. So if you look at the procedure of solving this question, the foremost requirement of solving this problem is the ability to convert this circuit into a Thevenin's equivalent circuit. If you're not proficient enough in converting circuits into their Thevenin's equivalent circuits, then you might find it difficult to find the load resistance which will dissipate the maximum power. So let us find the value of VTH, and in order to do so we'll need to redraw the circuit with the load resistance open. And the point over here, let us say XY, the voltage here would be VOC, which is equivalent to VTH. In order to find the voltage, this open circuit voltage, we'll need to find this current. Let this current be I2, and let this current be total current I, and this current be I1. Now the total current I flowing out of this voltage source can be calculated by the simple formula total voltage upon total resistance, and total resistance is 5 plus 1, they are in series, and it is parallel to 2, and further it is in series with this one, and that will come out to be 4 by 5 by 2 or 8 by 5 ampere. And if the total current I is 8 by 5 ampere, then I2 can be easily found using current division rule, where the total current flowing into this node is 8 by 5 into opposite branches resistance is 2 upon opposite branches resistance 2 plus my own branches resistance is 5 plus 1. So that gives me a current of 2 by 5 ampere. Now it is important to find this current because we'll take up this loop to find out the value of VOC, and VOC obviously is VAB. Now let us say this point is A and B, so the voltage here at this point plus this 6 volt will give me VOC, and the voltage is easily found out 2 by 5 into the resistance value, which is 1. Plus 6. 32 by 5 volt is VOC or VTH. This is one and the same thing, so we're going to put this thing over here. Alright, now in order to find the Thevenin's equivalent resistance, we'll need to remove all the voltage sources. So we're left with this circuit. All the voltage sources are short, and we'll calculate RTH looking from the open terminals of the load. And I'll label the resistances once again. So RTH is technically 1 parallel 2 plus 5 and then further it is parallel to 1, which is equivalent to 17 by 20 ohms. You could see this calculation for yourself, or 0.85 ohms. So the answer to the first question is, what should be the value of R? So the value of R should be 0.85, which is the value of RTH. So the value of R should be 0.85 ohm in order to dissipate maximum power. And what will be the maximum power? P max will be, of course, the total voltage is, we can use the formula VOC square upon 4R. So 6.4 square upon 4 into 0.85. This formula is discussed in the previous tutorial, and these are ready reckoner formulas, super important, and that is how we solve a numerical problem where an unknown resistance needs to be found. The value of unknown resistance need to be found in order to get maximum power dissipated at the load. And in this numerical we are focused on two things: critically solving a network to its Thevenin's equivalent circuit, and once we do that we find the value of load resistance and the power dissipated. And I hope this numerical problem clears up a lot of issues that you face in solving numericals on maximum power transfer theorem. And if this video helped, give it a thumbs up and consider subscribing to the channel. I'll see you around. Have a great day ahead. Bye.